Hello all, let's talk about the tolerances in this segment of the Module 3. Tolerances are basically the manufacturing limits on the dimensions that we assign on the solid model when created in a drawing. Basically, the tolerances are classified into two main categories. One is the bilateral tolerance and the second is the unilateral tolerance. The bilateral tolerance can be classified further into symmetric or asymmetric tolerances, as you can see from the figure on the right. If we have a part where we have assigned a dimension of, let us say, 75 plus minus 2, which can be classified as the bilateral symmetric tolerance because we are allowed to deviate in the plus or the minus side by 2 units. The bilateral asymmetric tolerance is when you have unequal values in the plus and the minus direction. So we are allowed to have this part pass through the quality standard by going in 2 units positive direction and 1 units in the negative directions, which means that if this part is fabricated with the dimensions of ranging between 74 and 77, then this part will classify or basically pass through the quality standards. The unilateral tolerance is when we have at least one of the directions the value equal to 0, either in the plus or minus direction, and that is called as a deviation. So an example of the unilateral tolerance could be something like this: 75 0, 75 negative 2, which means that we would like to have this part created with the edge length between 75 and 73 units. So plus or the minus tolerances are the ones which define the range for manufacturing. Typically, these standard tolerances are provided next to the title block in a drawing, and some of the times the typical values are also assigned because it is impossible to create a part with different tolerances assigned to different surfaces or edges. That would require a highly precise manufacturing operation to do it, and it will become very expensive as well. So for example, if we have the tolerances specified something like x plus minus 1, which means that if the dimensions are given in integers, let's say 50, then the tolerance would be applied as 50 plus minus 1. Or if the decimal places, number of decimal places is just 1, say point x plus minus 0.5, which means that if the primary dimension is assigned as 50.0, then the tolerance will be assigned as plus minus 0.5 for that, and so on. So you would notice the tolerances information assigned in the title block of your engineering drawing. Now, typical errors to avoid when we assign the tolerances on the dimensions is that we should never dimension the same distance twice. That is called as the double dimensioning. And it creates the problem when we assign the tolerances to the part. So for example, if you look at on this lower left hand side figure, the dimensions are assigned as 25, 25, 25, like a chain dimensions. And also if we assign the overall dimension of 75, then that creates the problem of double dimensioning. Because if we assign the tolerance, let's say plus minus 1 is the tolerance assigned on all the numbers, then on the top we see the resulting dimensions would be 75 plus minus 3, so it could be from 72 to 78. And on the lower side we can see that only one number is there, so plus minus 1 will make it as 74 to 76. So now if we have the part manufactured, let's say 78 resulting dimension when we measured from the top side, and from the bottom side, let's say it manufactures with 74 units. So we have a situation where this edge will no longer be a vertical edge, but it will be an inclined edge to accommodate 78 units measured on the top and 74 units when we measured at the bottom edge. Okay, so unless there is another tolerance applied, which will be the geometrical tolerances or the tolerances of the shape or tolerances of the form, then additional tolerances will be applied in order to make sure that the edge created will be nearly vertical, if not exactly the vertical. So the tolerances can be classified into different categories. There are tolerances on the dimensions, there are tolerances on the geometry, there are tolerances of the form. So in this video, we will be focusing on the locational tolerances and also the dimensional tolerances. Let's take a look at an example where we assign the dimensions using either the chain scheme or the baseline scheme. And if we look at the chain dimension scheme, the two steps are provided the dimensions of 25 plus minus 1 each, and the overall dimension is 75 plus minus 1. So we should not be assigning the dimension on this edge, which is let's call it as the length as A, and that length basically is called as the tolerance built up. So this particular edge is not directly assigned any tolerance, but the resulting dimension of the edge with the length A will be absorbing the tolerance based on the other dimensions. So this is the uncontrolled dimension, or basically this is a driven dimension based on the other driving dimensions in the part. So if we want to find out what could be the maximum value of A using the chain dimension scheme, so the maximum A will be possible only when we have the maximum overall dimension and the minimum inner dimensions. So it will be 76 as the maximum overall dimension, and the minimum overall dimensions could be 24 and 24. That will make it 48, right? So if we subtract 48 from the 76, then we get the value of 28. So 28 could be the maximum possible value of A if we are using the chain dimension scheme. But if we look at the baseline dimension scheme, as we know that there is a reference datum plane or the edge, which we take it as a reference or a zero value, then all the dimensions are assigned with respect to that reference edge. And the dimension of A is really controlled by the dimension up to the beginning of this step here, which is 50 plus minus 1. So this edge could be created with the dimension of either 51 and the lower range will be 49. And the overall dimensions limits are 76 and 74. So the maximum possible value of A in this case, when we assign the baseline dimension, would be 76. So the maximum overall, and the minimum inside, which is 49. Okay, so that comes out to be 27 as the maximum possible value of A. If we look at the minimum values of A, then we have to go in the reverse way. So minimum A will be possible when we have the minimum overall dimension and the maximum inner dimensions, which will be 26 plus 26. That will make it as 52. And once we subtract 74 minus 52, we get 22 as the minimum possible value of A. If you look at the baseline dimension here, it will be 74 minus 51, which is the minimum overall and the maximum inside. And this will come out to be 23. So now if we look at the difference between the chain and the baseline dimension scheme, we notice that the unreliability factor here is of 6 units, 28 minus 22, which is 6 units. And the unreliability factor in the baseline dimension comes out to be 4 units, right? So what that means is that we have better control over the tolerance built up surfaces if we go with the baseline dimensions in this problem. And there is more unreliability in terms of resulting dimensions for the chain dimension scheme. Again, let's take a look at another example where we have 210 as the overall length and the individual lengths are also assigned. We need to apply the tolerance of plus minus 2 in this case, and we need to figure out what are the resulting dimensions for this length of the edge E if we use the chain dimension or the baseline dimension scheme. So let's do these calculations. If we write down the maximum and the minimum possible values for the individual dimensions based on plus minus 2 tolerances that we are applying, the resulting numbers we can easily calculate, and let's place it over these individual steps, and let's work it out with first the chain dimensions. So for the chain dimensions, the maximum value will be the maximum overall and the minimum inner one. So the maximum overall is 212, and the minimum of the individual dimensions when we add them up will be 58 plus 68 plus 18 plus 28. That comes out to be 172, and when we subtract 212 minus 172, we get the maximum possible value using the chain dimension as 40 units. Let's again work with the minimum dimension for the edge E using the chain dimension scheme for the minimum possible value of E, and in this case we need to go the minimum overall and the addition of the maximum inside dimension. So this will be 62 plus 72 plus 22 plus 32, and this number comes out to be 188. So 208 minus 188 will result into 20. So these are the maximum and the minimum possible values for the edge E as 40 and 20. Now let's work these numbers for the baseline scheme, and in the baseline scheme again the maximum overall, which is 212, and the distance from the baseline edge up to the beginning of this step for the length E is 180 when we add A plus B plus C plus D, and applying the tolerances of plus minus 2, that comes out to be 182 and 178. So 212 minus 178 will give us the maximum value for baseline scheme, and that comes out to be 34. And for the minimum value, it will be 208 minus 182, which comes out to be 26. And so we can see a clear difference in the baseline and the chain scheme here. So if we really calculate the nominal dimension of E based on the nominal values, which is 60 plus 70, 130 plus 2150 plus 3180, subtracted from 210, which comes out to be 30, and I'm putting them in the parentheses because I don't want the tolerances to be applied on that number because it is the tolerance built up age. So for the nominal value of 30 using the baseline scheme, there is a range of 8 units. So we can say that the tolerance built up is basically 30 plus minus 4. And here in the chain dimension scheme, we have the range from 40 to 20. So it means it is 30 plus minus 10. And we can see a big difference in the unreliability of the tolerance built up age in the chain dimension as plus minus 10. However, for the baseline scheme, it is plus minus 4. So clearly the baseline dimensioning scheme, if we use for this particular problem, then we have less unreliability in the tolerance built-up age of 30 plus minus 4 as compared to 30 plus minus 10 for the chain. Also, when we look at this example where we assign the baseline dimensions, each dimension, as you can see, for the locating, for locating the center of the holes on that plate, are individually controlled by the the two dimensions for the center of that hole. So even if there are tolerances applied on, let's say, one particular hole, that is not going to affect the location for the other holes if we use the baseline scheme as indicated here. But if we were to use the chain dimension, then all the dimension would have been applied as going in form of a chain. So all these chain dimensions would affect one another. So if there is a tolerance, a big tolerance applied for, let's say, one particular hole, that is going to affect the location for all other holes because they're all connected together. And that is again the emphasis on the baseline dimensions advantage while fabricating this part. All right, so now let's take a look at how to choose a shaft for a hole that is toleranced. In this example, we want to design a shaft that must pass through this rectangular plate, and this rectangular plate has a hole through which the shaft is supposed to be passing through, and the hole, when we manufacture it, has the locational tolerances in the X and the Y direction. Along the X direction, we have the tolerance of 5.0 plus minus 0.2 inches, and in the Y direction is 5.0 plus minus 0.3 inches. So the center of the hole, when we create, it could vary along the X direction by 0.4 units because it is plus minus 0.2, and along the Y direction, the hole can be created with the variation of plus minus 0.3, meaning total variation of 0.6 units. So the hole can be created anywhere along this rectangular tolerance location zone, which is highlighted or magnified here, and 0.4 by 0.6 becomes our tolerance region, where anywhere in this rectangle the hole center can be created. Okay, so that's the locational tolerance. In the worst case scenario, the hole could be created with its center on the 4 vertices of this rectangle. That is the extreme condition. So, and there are 4 possible scenarios for that extreme condition. In addition to that, we have the tolerances applied on the dimension of the hole as well, which is 1.100 plus minus 0.0500. So if we look at the maximum value of this hole that could be created would be 1.150, and the minimum value that could be created could be 1.050. Okay, so that's the maximum possible value of the hole that can be created, and the minimum possible value of the hole, which will be 1.050. So we need to find out what will be the dimension or the maximum dimension of the shaft that will always pass through the center of this rectangular plate. In order to have a perfect alignment, we have no choice but to pass the shaft exactly through the center of this plate. But we really have no control on where the hole will be created with its center, and what would be the dimension of the hole. So we need to consider that and do the calculations for finding out what could be the most, the maximum possible value of the shaft that can be created. So the equation for this is shaft max equal to hole min minus the DTZ. DTZ is the diagonal distance across the tolerance zone. Our tolerance zone is 0.4 by 0.6, and the DTZ is the diagonal distance, which means that in order to calculate that, we will have to take the square root of the sum of the squares of the two perpendicular distances, which is 0.4 and 0.6. So square root of 0.4 square plus 0.6 square gives 0.72. So the diagonal distance is 0.72. And if we want to find out the maximum possible shaft diameter, we need to be considering the worst possible condition, which is that we need to consider the minimum value of the hole that could be created, which is 1.050. So 1.050 minus 0.72 will give you 0.329 inches. And that is the maximum possible diameter of the shaft that will always be able to pass through exactly the center of this plate, no matter where the hole is created. And if we draw the circles of 1.050 from all these four corner vertices, which are representing our extreme possible locations for creating the hole, and if we create those 1.050 diameter holes on these four corners, we will find that the common area to all these four circles will be a circle that has a diameter of 0.329. And so it doesn't matter where the hole is created and whatever the dimension of the hole could be created. So in the worst case, if the hole is created, let's say in this topmost left vertex with 1.050 diameter, even then the shaft of 0.329 inches will be able to pass through that, because it has to pass through the center. The same thing for the other vertices as well. Even if the circle of 1.050 is created on one of these vertices, even then it will always be guaranteed that the circle of 0.329 will always be able to pass through the center. And that is what we call it as the maximum diameter of the shaft that can be possible, considering all the extreme and the worst conditions. So let's verify this calculations of the maximum possible diameter of the shaft using the SolidWorks. And I'm going to create a new sketch. I'm going to set up the units in inches and create a rectangular tolerance zone of 0.4 by 0.6. And then I'm going to create 4 circles on 4 different vertices of 1.050. I'm going to repeat the procedure for the other remaining vertices as well, and I'm going to just use the constraint of making the equal dimension for all the other remaining circles. Once we do that, then we have this common area that encompasses all the 4 circles. And now if I try to create a circle from the center that coincides with the circles that we create, any of the circles, if you see that we can create a tangent, something like this. So this is the circle that is common to all these 4 1.050 circles that we've created, and that is the maximum possible diameter of the shaft that will always be able to pass through this center of the plate. And if I try to see its dimension, it will be 0.329. Of course, this will be the driven dimension. So I'm just going to cancel it, and that's how we can verify this using the SolidWorks. I've just changed the units, and again I'm gonna do the smart dimension to this, and now we can see that it is 0.329 as we've calculated theoretically. So now let's take a look at another example which is very similar to this except the numbers. So we have the tolerance region of 1 millimeter by 2 millimeters, and the hole dimensions are having the tolerances of 11 plus minus 1, which means the hole could be created as either 10 millimeters as the minimum size or the 12 millimeters as the maximum size, with the tolerance range of 1 by 2 millimeters as the tolerance zone. So we need to calculate what is the maximum possible diameter of the shaft that will always pass through the center of this plate. So let's use that equation. S max equals to hole minimum minus the diagonal tolerance zone distance, DTZ. So in this case, the DTZ can be calculated as equal to square root of 1 square plus 2 square, which is equal to square root of 5. Square root of 5 is equal to 2.236, and if we calculate the S max based on these numbers, we get hole minimum, which is 10 millimeters minus 2.236, and that is equal to 7.763. So 7.763 millimeters will be the maximum possible diameter of the shaft that will always pass through the center of the hole. And let's verify that with the SolidWorks. Going to start a new part, and let's use the units of millimeters. Let's use the front plane to sketch on it. First, let's make the rectangular tolerance zone, which is 1 millimeter by 2 millimeters, and then let's create 4 circles of 10 millimeters diameter. So I'm going to smart dimension it, make it 10, and then I'll create 4 additional circles, the remaining 3 additional circles, and I will use the constraints of equal length for all these, or equal diameter for all the circles. So once we create the possible locations of the holes with the minimum hole diameter of 10 units from the extreme corners of this rectangular tolerance zone, then I will try and match up by creating another circle by looking at what is the maximum possible diameter of the circle that will be common to all the 4 circles. So once I click here, this is the maximum diameter of the shaft that is possible, that will always pass through the center. And if I smart dimension it, it will be 7.76, which basically matches up with the theoretical calculations that we just have. So that is how we can calculate the shaft diameter for the toleranced hole. So 7.76 millimeters is the diameter of that shaft. And that concludes the basic introduction to the tolerances in this module. Thanks for watching, and I will see you again in the next video.